Okay, so it's a pleasure to welcome Hugues from CES Akle and Beijing CSRC, and he'll talk about hydrodynamics and fluctuations in dilute aligning dry active matter. So we go.
Okay, thanks for the invitation. So as I was saying just before we officially started, I feel like an outsider in this crowd, and I tried and made an effort to say things that are introductory and yet say currently, true results or updated results on that. I may slip away, and if I say something that is suddenly unclear, please interrupt. So this is, I will spend some time explaining the title, of course, which seems a bit long, but don't worry about this. And this is work, I'm trying to change screen, yes, slide. This is work that has been done, in fact, mostly by Benoit Mao, who is among us. He is now at Göttingen, at the Max Planck Institute, and with other people you may know of, but it's mostly the work of Benoit today. And so this is the outline. Before I forget, there are not too many references, in particular to our own work in these slides. So if you have questions for references or some science questions, or even some PRL questions, because I'm also the lead editor of PRL, don't hesitate writing to me, or we can talk after the talk. The outline is very simple: an introduction to active matter, and in particular to the kind of active matter we'll be talking about in more detail, an update on the Vicsec model and tornado theory, which were sort of starting points for this whole field, and this is basically what I'll be talking about, in fact, still today. Then I would say the bulk of the talk in this context will be how do we derive kinetic and hydrodynamic theories for that sort of active matter, and in particular via what I call here Ginzburg-Landau route. So this will be about obtaining the equations, or some approximate equations. And the last part, which I call faithfulness of kinetic and hydrodynamic equations that were just derived, so to speak, we investigate how faithful they are to the original starting point, which for this talk will be the Vicshag model. Okay, so 4 parts. This is the classic slide for almost every talk on active matter, but I thought for this audience it's necessary. What do I mean? What do people mean by active matter? They mean systems that are out of equilibrium, but where the out of equilibriumness, is at some local level in the bulk. Individual objects, units, particles spend energy to typically convert energy into mechanical work, and so produce motion of some sort, not just random thermal fluctuations. And I'm myself mostly interested in, of course, the collective behavior that can emerge from such a large, vague, but very generic definition. And here you see objects of various scales. Here you don't see, but you have many, many, many microtubules displaced in 2D by a bunch of complexes of molecular motors. So these are subcellular, nanoscale, almost microscale objects. These are bacteria seen by fluorescence, so these are micron scales. Here you have other microtubules. Here you have synthetic active colloidal particles, micronic size particles. Here you have millimeter size shaken granular particles, which are not spherical. And so they have some asymmetry, and this asymmetry, when shaken properly, makes them move, and collectively they do also kinds of interesting things. And here you have, of course, animal groups with the classic Starling flock picture. Okay, so on all scales, in various contexts, living and non-living, there are many systems with more or less control on them than many, many, many active matter systems. Okay. I decided to show you first 2 examples which have nothing to do with my talk, because I like them. They are made mostly coming from work by collaborators of mine in China, and it will help me precise what I mean by dry aligning active matter. Here you see in real time bacterial cells, which are marked by fluorescence, at the edge of a growing colony. So the colony is growing on classic agar plate, etc., growing very, very slowly. And about on a layer at the rim of this colony, in this case, for about 1 or 2 millimeters, you see dynamics like this, where it's quasi two-dimensional. It's not quite a monolayer, but the cells are trying to move in the fluid with their flagella, but they can't because it's too dense. They're basically jammed. Nevertheless, because they align, and you see alignment here going on, and you see the cells are elongated, and so when they're pressed together in some high density, they align nematically. It's hard to tell where is head or tail here because you don't see the flagella. But they collectively, because they are aligned, they're able to set the fluid in which they're trying to do this into motion. And what basically is recorded here in the lab frame is a motion of a fluid, which of course advex and rotates the bacteria. So this is a system where even though there is friction with the substrate here, this agar gel, you cannot neglect the fluid, of course, in which these things are not even moving, but the fluid which displaces the active agents. Another example, so this is to show that we can extract from this, nematic field, the velocity field, etc. But I will skip this. Another example, which I like, recent and almost published, is artificial colloidal particles. These are spherical particles of about 5 micron in diameters, they're lying at the bottom of a dish filled with some weakly conducting fluid, and there's a transversal vertical electric field, DC field applied. And the field is strong enough, it's well known that such a particle, due to complicated electro-hydrodynamic effects and instabilities, can start rotating, but because it's on the substrate lying on the bottom, it will actually roll on the ground in some arbitrary direction. And when you have many of them, it has been known for some time that they can actually flock, meaning go together in some collective motion state, okay, and some spontaneous symmetry breaking at the collective level. And here I'm showing you a regime of this system where individual particles, isolated particles, actually cannot move. The field is not strong enough, but when they're close enough to each other, they can set motion can start, and in particular, among the many interesting phenomena that occurs in this regime, you see these very large, sometimes much larger than this, self-standing vortices forming and rotating forever in the system. So here again, the motion is a complex interplay between mechanical friction, high electro-hydrodynamic forces, fluid dynamics, you name it. And in fact, the very details of this are not very well known yet, in my view. So this is a system where you cannot get rid of the fluid in particular, of course. Now, active matter has been possibly the fastest growing subfield of statistical physics in a loose sense. And this is my one way of representing some of the directions into which this body of knowledge is growing. People distinguish, something I already alluded to, between wet and dry systems. Dry systems, which I will be talking about, are systems for which the fluid surrounding the moving particles is, can be faithfully neglected, safely neglected. Okay, which is not the case of the two examples I've shown you. Now, pure swimmers in a bulk fluid would be considered like a strictly wet system. And then in between, you have systems like those I showed you, which are in contact with the substrate in some sense. And that makes them sort of a halfway between wet and dry. And the major interactions that people have considered, especially at the theoretical point of view, are steric repulsion between objects and some alignment, which may be coming from the shape of the particles or for some other forces. And of course, classically, people distinguish dense and dilute systems, okay? So there are many missing directions, and this field is really becoming too rich to summarize in a talk. Now, as often, the limit cases are those where you have maybe limited direct experimental relevance, but they are those which, on the theoretical viewpoint, have been most studied. So the most advanced works at the theoretical level of on limit cases. Here, I on this convenient cube, I just put two. Bottom right here, the MIPS and ABP, all these acronyms means persistent random walkers that interact strictly by pairwise repulsion forces. That will be what I mean by these acronyms. And even though there are just repulsive forces, they can phase separate in what is called motility-induced phase separation, MIPS. Okay, so I will not be talking about this. To some extent, this is a simpler system than what I would be talking about, in which we are here in the corner of a cube where we have a strictly dry system also. The only interaction between objects, active particles, is alignment, local alignment, in competition with noise, say. And we consider some kind of dilute limit implicitly, in the sense that these particles are taken to be pointwise or quasi-pointwise. And so whatever interactions they may have is not very important. It's so dominating by the alignment. So this is dry aligning dilute active matter, which acronym for this is DADAM, which is kind of fun. And I've been trying to use this for a few years now. Okay, so I will be talking about DADAM only. So this corner of this cube. Okay, and one message at the end is that even though I'm looking at a limit of a limit of a limit case, the phenomenology of even the simplest models in this sort of setting is still not completely known and very rich, in fact. And we're trying to do hydrodynamic and kinetic approaches to this, okay? So in fact, one, and maybe the best known simple model, particle model in this DADAM setting is a Vicsec model, now called Vicsec model, introduced in 1995 by Vicshag and collaborators. So in words, these are, again, point particles moving at constant speed. They don't have an intrinsic polarity, but they just have a velocity. The velocity is only local, the only degree of freedom attached to the particles, and the velocity direction, in fact, because the speed is constant. And the interaction is a local alignment within, say, unit distance, with whoever is nearby within unit distance one, including yourself. You do a local average, weighted or not, of the directions of all the particles in the neighborhood. That gives you a local mean direction, and which is the direction of motion at the next time step if you do this at discrete times, but you don't have to. And this is in competition with noise. So typically after calculating this mean local orientation, you would add a random angle, from some distribution of noise. Okay. In some sense, this can be seen as a flying in 2D, a flying XY model. Take your favorite XY model on lattice or off lattice, something like that, and now you force the spins to move at constant speed. Typically, this brings non-equilibriumness, and then exchange positions are never changing, etc. So this self-propulsion part, it's not so much the self-propulsion, and as argued by Sriram Ramaswamy recently, that is key here to new phenomena. But it is in the simplest model, and the simplest systems we can think of are those of active self-propelled particles, like the Vicshag model. So I do encourage those of you interested in the most advanced views on these things to look at recent works by Sriram, whose name I see here in front of me, so I cannot forget him. Nevertheless, in '95, so Vicshag and collaborators didn't do much except from introducing a view of collective motion, and they were thinking about bacteria and animals, etc., as some spontaneous symmetry breaking phenomenon, and they tried to strip down the whole thing to the simplest model they could think of, and that's it. Point particles, constant speed, local alignment, some noise, and that's it. So of course, if you have low density of particles, as shown here on the snapshot on the left, or strong noise, basically you have these persistent random walkers, and the interaction is not strong enough and not persistent enough so that any significant orientational order can emerge. On the other hand, if you have high enough density or weak enough noise, and not necessarily zero noise, you can have a fluctuating but globally ordered, polarly ordered phase. Here the global, I don't know if you see the individual arrows, but the global direction is more or less vertical, okay? In a finite system, this global direction wanders, but as you increase system size, this wandering is slower and slower. So implicitly, Vicshag considered that this gives rise to 2D long-range order in his 95 PRL paper here. And that paper, after defining the model, focuses on the transition from disorder to order, orientational order, and it is presented on the basis of numerical simulations as a continuous new critical phase transitions in 2D non-equilibrium systems. So that's 95 Vicshag. I'll come back to this, of course, much later. In the same year, John Toner, Hydrodynamics, inspired by Vicshag, wrote down from symmetry and expansion, gradient expansion type of setting, fluctuating hydrodynamic equations for this system, for the Vicshag model, in which you have a conserved density field advected by a velocity, conserved density field advected by a velocity field, and the velocity field evolves by a Navier-Stokes-like PDE here, or equation here, with this classic Navier-Stokes term here, but with an arbitrary coefficient lambda 1 plus two other terms which are allowed by symmetries. Alignment between the particles does not preserve momentum, so you are allowed to write down all these terms. I mean, these terms can also be coming back from some free energy functional. So yeah, anything that's allowed with two V's and one grad or here, okay, by symmetries. That's the way they thought. And a non-Navier-Stokes part, and the key part here is this 5,4 Ginzburg lambda V minus V cube term, which for mu positive and psi negative gives the velocity field a mean value V0. Okay, this is coupled by an isotropic pressure to the density field. There is some diffusion here on some viscosity, if you want here, anisotropic viscosity terms. So all these terms are necessary in the kind of renormalization group approach that John Toner and Hydrodynamics actually did. What they did is they wrote this down, and then they assumed that you have an homogeneous ordered phase fluctuating for everybody moving. V is the constant equals to this V0 given by this balance of Ginzburg lambda terms. And they studied robustness of this solution. There you see there's a noise term here, F, which is an arbitrarily additive noise that and then they did some RG dynamic, so-called dynamic RG procedure to study the stability of the ordered moving phase to fluctuations. And they predicted a general scaling for the fluctuation, for the correlations of fluctuations, in which you have generically long-range ordered anisotropically scaling fluctuations. I will not show you the details of this. They noticed the breakdown of linear hydrodynamics below dimension 4. And their analysis, which is erroneous, but at the time, the analysis led them to conclude that there is true long-range order even in 2 dimensions in this system, contrary to the XY model and other equilibrium 2D systems with spontaneously broken rotational symmetry. So right from the beginning, you see this was about, and also in the works of Sriram Ramaswamy, this was about long-range correlations of fluctuations and how you can describe them, hopefully, using hydrodynamic theories. Okay, so but here the theory was just written down. The calculation was done under some strong RG hypothesis, as you can guess, and that's where we were in 95. Already, I would like to remark here that if you do this, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever, 10, 12 transport coefficients, which in fact should be functions of a local density, because this is typically a compressible fluid. And of course, you lose the connection to the microscopic world. Even though this is pretending to describe a Vicshag model, how do you relate the few parameters of the Vicshag model to these many coefficients? So it's interesting to be able to derive hydrodynamic theories from the microscopic world, which I will do in this talk. Okay. So a lot of progress has been done since then. The remainder of this talk is focused on Vicshag toner 2 kind of class. But for those of you interested in nematic alignment, like for this bacteria I showed you, similar results hold, and they are more or less available. So, but I will not talk about this at all. So the second part is, what do we know now about the Vicshag model and the toner 2 theory, the toner 2 theoretical results? And I will proceed to this. So in 95, a problem was presented by Vicshag and actually also by toner and 2 as a classic order-disorder transition magnetic systems, but in a non-equilibrium setting. And it took a rather long time to realize, and especially have clear evidence, that the best way of looking at this transition that I showed you is not the direct transition from, like in magnetic systems, but is a framework of liquid-gas phase separation. And this was first shown actually in the so-called activizing model by Solon and Thayer, and I will show you this in the next slides. The physical mechanism behind this is the feedback between the local density and the local order in these highly compressible fluids. So to be more specific now, no, not quite specific, I will go to the Vicshag model. These are very general slides that apply to all kinds of Vicshag-like models. What you have, here, global density versus variance of noise strength, so to speak. As I said, for strong noise, low density, you have a disordered gas. That's a word that we use from now on. But for large enough density and low enough noise, you have an ordered, orientationally ordered phase, which I will call the liquid. And the transition is not by a single second order critical line here, but in between there is a whole phase, or coexistence phase, in which bits, little patches of dense ordered liquid stand out of sparse remaining gas, really like a phase separation scenario, except that here, the symmetry of a liquid, of course, which has long-range order, or intentional order, or quasi-long-range order in some cases, is different from the gas, which has, rotational symmetry. So the critical point in a classic picture, you would have a parabola here, and a critical point at the top of the parabola. Here, this is not possible. In some sense, the critical point is sent to infinite density, or 0D, or limit if you want. So in pictures now, this looks like this. I've shown you this. So, strong noise, or low density, high density, and what Vicshag saw, so to speak. But in between, in the same system, by the way, here, same size, same system size, basically, in between you have, in a smallish system like this one, particles have spontaneously arranged themselves into a single here, traveling band, we're traveling from left to right here, with a very sharp, rather sharp front and some not so sharp tail, moving at constant speed, not too far from the nominal speed of particles, in a remaining gas. Of course, particles in the gas are recruited in the band regularly, and the band itself leaves back some particles, etc. Now, on a larger system and much larger timescales, this looks like this. Interesting. That's not working. I'm not sure what I can do. Let me try to show this to you. We didn't check this movie, so I will go and present a view and see whether that can work here. Maybe it is the sorry, I'll go back to slideshow and I get rid of the pointer. Vicshag. Hello, I'm stuck. We'll get rid of this. Okay. What do I do? Arrow. Maybe this will be better. Yes. So here you don't see really a movie because every frame is separated by many, many time steps. So it's a kind of stroboscopic view of a system, but you see that here we have millions of particles and millions of time steps roughly over very long time scales. These bands are not just one band, it's many bands, and they arrange themselves into a fairly regular symmetric arrangement with compression modes that you saw in the transient. I will show it again for you. So that's typical of the coexistence phase for the Vicsec model. And that phase occupies actually a fairly large region of this density noise phase diagram. Now, today, in fact, we have started exploring the coexistence phase more seriously than was done before. And this is ongoing work, but I'm just showing you some nice pictures here of configurations made of bands, which are actually robust, stable in arbitrarily large systems for finite regions of parameter space, which we're trying to make sense of. But here you have three systems of bands on top of each other. If you see my arrow now, I try to go back to the pointer. If you see three systems of bands superimposed, each of them moving regularly. Here you have bands going leftward for the blue and rightward for the red, coexisting. So these are lanes of bands, and here you have not even, two systems of band, but one is not even covering the whole space here. And this so-called cross-C thing. So these are still being explored. These phenomena, we already know that they require pretty high order hydrodynamic terms in hydrodynamic theories to be accounted for. And we're currently—
So Hugo,
yes.
Just a question. In this middle picture, you see bands that are going both to the right and to the left.
Yes, yes. And so this interface here is actually subjected to instabilities when you have a system very long this way. But if you extend only this direction, you have very interesting pattern forming thing. It's not coarsening at all. And I don't have time to discuss this, but so this is, I would say, asymptotically stable for systems with aspect ratio much longer than in the transverse direction than in the direction of order, or order is this way or that way. But so yeah, they're very robust things. But as you noticed, and I didn't boast about this, but all these things require much larger system sizes and times, of course, than were studied before. So it's a never ending, it seems, discovery of more and more exotic subphases in this thing. Okay, so just to let you know that not everything is clear and dandy and known, even about the Vicsec model. That's the message here. Okay.
So one other question, sorry. So the three patterns are all in the coexistence region, right?
Yes. In fact, some of them may be even at the same parameters. I mean, I didn't check.
Oh, same parameter.
I chose. Okay. You see this one and this one. I know here it's slightly larger density, but they can coexist. We don't know to what extent. This is, of course, messy to do numerically, but for sure they can coexist at least by pair at some parameter values.
Okay. I think Sriram
has a question.
Yeah, I was just wondering, is it fairly well established now, at least, that the basic period of the simple striped phase that you have is set more or less by the wave number of the linear instability that you get just past onset, or is it very different? Or is it sort of still trying?
Well, if you pre-assume that the pattern you're looking at is a symmetric, and only a symmetric on one system of bands, so to speak, then yes, there's a single wavelength selected, and he says we have data on this. But now what we see is that almost everywhere in the coexistence phase, you do not necessarily have a simple spectic configuration. Even very close to the transition, you will find this, other things. So if you pre-assume that you have, so here, these things, they can come in different orientations of each of the subsystems of bands and so on, and so that the wavelength that you would define for each of these band subsystems can actually change.
I see, but I was wondering if when you look at the linear stability of the uniform flock, just past onset, you find a finite wave number instability from the analytical theory, from a simple-minded, right? Is the onset wavelength of these bands at least simply related to that, or is that not a good guide?
No, because
not a good guide.
In the phase separation scenario, if you have a large but finite system, the first thing that will occur if you wait long enough coming from the disordered phase is the nucleation of one band.
Right.
So the wavelength of this pattern is 0, the wave number of this pattern is 0, wavelength.
Right.
So it's really not in terms of, even though the linear stability analysis of Tono 2 and whatever remains the same and does show, well, it's a long wavelength instability, but of course it has a maximum, most unstable wave vector, and that wave vector is finite. Whereas, and that, one other thing I have to say, but that's going to be end of my talk or some part of or middle of my talk, is that we're talking linear instability here. So if you are in the linear instability region of the liquid, the wavelength may be in same order of magnitude. The linear stability, most unstable wavelength will be of the same order as what you see numerically up to coexisting patterns. But the first appearance of A band is near the gas binodal, which is away in the coexistence region where the liquid is actually linearly stable.
Right.
So,
okay,
all right. Sorry, guys, for the discussion between specialists.
Yeah.
Hopefully, this conversation will become clear if I manage to finish my talk. So in 2012, John Toner realized that his calculation, this RG calculation I mentioned, which was claimed to be exact at all orders in perturbation theory thanks to some extra symmetry, well, that calculation was not that exact anymore because many other terms without that symmetry were just as dangerous from the RG viewpoint as the one he considered. So no more exact results. So if you look at John Toner's 2012 paper, which is maybe the best way to enter this problem, and the crucial point where he says that, oh, yes, but the long range order is preserved because this coupling constant must flow, I don't know, negative or positive, it depends on how you define it. That crucial point to me is still not obvious. And to me, or Benoit, who have been thinking about this. So to me, at this point, we thought that is really, really time to do a numerical check of, which was not done seriously before, of the Toner 2 theory results, whether fluctuations have long-range correlations, whether they scale anisotropically, and so on. Another specialist wants to say something. So go ahead, Ananio.
Hi. Sorry.
Hi.
So I didn't understand. So the argument for the long-range order was simply that the noise cannot be renormalized simply because of the nature of the nonlinearities. And the diffusivities are renormalized upwards. So that was simply the argument for the long-range order. So why do you think that will fail? Ultimately?
Well, I will have to double check with Benoit what I'm saying, but if it's obvious for you that diffusivities are rescaled, this way or that way, then it's true. But what is the calculation that shows that they are rescaled in that direction and not the other one? It's
sure,
not.
That is one loop.
That's a key point. That's a key point. If you assume this, of course, it flows to, and then you get a negative chi exponent and so on. So for us, it's still. I would, if you push me a bit, I would disagree with John that the long-range order result holds. I mean, if you assume this, then it holds. That's
okay.
Okay. Again, for specialists. Okay, so it's time for numerical checks, and we did this in this PRL paper with Benoit Mao, and I will show you, I will skip this and I'll just tell you what's written here with the images that follow. First of all, a simple thing that even Vicshag should have done and could have done even with modest numerical means at the time is to check that there is indeed long-range order numerically in the Vicshag model. And so here is a plot, log plot of global polar order parameter versus size. You see it's decreasing with system size, but there's upward curvature, and this can be scaled as going to an infinite, well-defined finite value as a power law, which is one of the exponents. And so that's a simple thing that even Vicshag could have done, should have done, in fact, if you think about it, if we think now about it. And that shows clearly for somebody doing numerical simulations, so it shows clearly that you have nice long-range order, and it is approached algebraically as it should within the theory. And that gives you actually a combination of the exponents that John has been talking about. And that involves only measuring a global quantity, not even the susceptibility, so it's easy. Less easy, much less easy, is to check that even the linear hydrodynamics part, the sound modes predicted, so they predicted anisotropic sound modes in the liquid phase, in the toner 2 liquid phase. That's the prediction of toner 2. That's actually verified quantitatively up to 1 fitting constant by measuring, I don't have time to discuss this, in very large system, very careful space-time Fourier spectra, and the motion, the scaling of these peaks with wave number here in the longitudinal direction. You can see that this scales linearly with the wave number, so you can define indeed sound speed, and the sound speed, if you represent them this way on some angular polar plot, they superimpose. They are the points, the green, the red and blue points are numerical results, and the cycloid below is the prediction of toner 2 theory, so that fits very well at the linear level. But of course, there's breakdown of linear hydrodynamics. From that sort of thing, if you measure a peak width, you can estimate a Z exponent to be more or less 4/3 here. And other exponents have been measured from the scaling of, so first of all, fluctuations are correlated long range, and they scale anisotropically. And so you have to do measurements in precise directions in Fourier space for the correlation functions. And here's a summary of predictions, so-called, used to be exact predictions by toner 295 for the scaling exponents, which I don't want to define here. The Z exponent is the one you can think of. Here we find this instead of 1.2, not too far. And the crucial exponent is chi. If it's negative, you have long-range order. And we find that it's even more long-range order than toner 2 predicted, so to speak, but there's a 50% difference here. And the surprise really was that the anisotropy exponent, which is the difference in the scaling exponents between the longitudinal and the transverse directions for the fluctuations of velocity or density, by the way, instead of being predicted to be 0.6, is actually so close to 1, meaning no anisotropy, that we cannot really rule this out. And this is, so here we have numerics. The numerics is worth what it's worth. It's fairly extensive given today's means. We have this theory that is not exact, but anyway, it's perturbative and so on. We are really in need of a more serious theoretical approach to this. Okay, that's where we are for the liquid phase. Something else that was done, and here I will accelerate a bit because I'm really worried about the rest of the talk, is you can look, if you take a default toner 2 equation like this, you look at it in 1D, you look for solutions that are homogeneous in one direction, Y, so it depends only on X. You look at a scalar field then, and you look for solutions that are moving in a frame of reference at velocity C and are stationary in that moving frame of reference. Then you transform your PDEs into some ODEs, and you can solve these ODEs or look at them. It's a simple two-dimensional dynamical system that 2 degrees of freedom dynamical system that you're left with. You can do this, and you can systematically explore solutions of these dynamical systems, and you find that typically at fixed parameter values, you will have a one parameter family of band-like solutions or periodic solutions in dynamical systems, a single homoclinic orbit and a single heteroclinic orbit. So this is all very classic, simple dynamical systems kind of approach. The next step is these are solutions. This is existence of some solutions like this in the PDEs. You can look at the PDEs, and they actually are coexisting and linearly stable. And indeed, that's what Sriram mentioned first. If we put noise now to these PDEs, so the deterministic hydrodynamic equations, you can see there's a selection of one single solution among many coexisting one at the deterministic level. This is another pending problem. How do we understand this properly? Okay, I'll accelerate further and further away. So now what we'd like to do is really to try to connect the microscopic to the hydrodynamic world or kinetic world. There is one special case here. There's one work, and I refer to this PRL here by people you may know, Erinu, Bodino, Tyre, and a student here, where they, from a specially designed lattice gas, designed to be an activizing type of lattice gas, they do a derivation using well-known techniques of deterministic equations here in 1D, which are exact hydrodynamic equations for the lattice gas that they consider. So this is one case I know where exact hydrodynamics in the sense that has been used in this audience mostly is known for a very special case. But now we would like to not have to rely on two special microscopic models and be able to treat, pretty much any simple particle, active particle models. So people do this using usually connecting the microscopic to hydrodynamic. They do this via kinetic equations for one body probability distribution function F using some strong approximation. So this is a third part of a talk. I will accelerate further. But I present two ways here of doing this. There are more than that. These two ways are the one I prefer and the simplest ones. There are more complicated but not so more successful ones that I don't want to talk about. One way to start is to consider a Boltzmann equation. So now the microscopic starting point is particles that run and tumble, constant speed, and a dilute limit in which you only consider binary collisions, and you invoke molecular chaos, which is a very dangerous thing to do in this setting, because once you align, you stay aligned for a long time, possibly, and that should rule out the validity of molecular chaos. So this is a very strong approximation. Nevertheless, you proceed. If you do this, you can write a Boltzmann equation, which is only for this one body distribution function F, okay? There are some details here, which I skip over, okay? Another approach, simpler, is to start from a Longrange type of continuous time Vicshag model here, where you have alignment like in a Chromato model, some noise, some rotational noise, diffusion rotational noise here. And you follow, for example, Dean and to derive a stochastic Smolikovsky equation for F, the same F more or less, except that here it's a combination of delta functions. So you have to take in the large density limit some continuous version of this. This is where you do again strong approximations, and you end up with something like this, where you have, it's very similar to the Boltzmann equation, except that here you have an explicit noise term here, which I will neglect afterward, and an interaction term which just reflects the sign function of the alignment. Okay, so these are two routes to go to a kinetic equation for this one body function F. What do we do afterwards? What do people do afterwards is that we expand F in Fourier modes of the angular variable theta, so Fk's. I forget about the hat later. F0 is the density, F1 is rho times the polarity field, F2 is a nematic field, and so on. And I keep complex gradients here for simplicity of notation in 2D. This is restricted to 2D now. And here are my kinetic equations expressed in these modes Fk. So these now hierarchies of coupled PDEs for the Fks. For the Boltzmann, you have this case. For the Shmolikovsky case, you have this. There are, this part is the same. And I have scaled out everything I could scale out here. And you see that the interaction structure is very different. The Boltzmann couples basically all fields together, whereas here you have a limited coupling between fields. Okay, the structure is different. Nevertheless, what we do next is that we do these also. These are kinetic equations. And now we go to hydrodynamic level by truncating and closing these hierarchies. And we do this using techniques that are well known from, weakly nonlinear analysis, amplitude equations, what I call here Ginsburg-Lambda truncation. So we can find for each particular problem, we look at a well-defined unique scaling ansatz. So each field, each gradient is assigned some epsilon power, and you just truncate and close at typically at order 3, if you're not mistaken, from the first non-trivial order, and then you obtain well-behaved PDEs, coupled PDEs. Here, in this case, for the continuity equation, which is exact and which is written in this complex notation. Sorry. And here, the Toner 2 equation takes this form, coupled to the density by this very simple pressure term, if you want, the Ginsburg-Lambda form that Toner and 2 had put down. The viscosity and 2 extra and 2 of the 3, some combination of the advection terms that are characteristic of these fluids, so to speak. So you can do this, and you arrive at these equations, these very same formal equations, whether you come from Boltzmann or Shmolikovsky. The only difference is in how the coefficients here are expressed in function of the microscopic parameters you started from, okay? So you can study these things, now varying the microscopic parameters of the original microscopic starting point. So these are slightly simpler than Toner 2, but slightly more complicated than this exact hydrodynamic lattice gas hydrodynamic theory that I showed you before. We can think about this. The last part, I'm not sure how much I can go on, but last part is
Hugo,
okay. Yeah, tell me.
Sorry, question. Yeah, so you said it's simpler. It has less terms than the Toner 2 equations.
Yeah,
but does it still capture all the physics, or those terms?
Yes. This is it captures all the physics, and it captures the phase diagrams. It captures more of it. Toner 2. It depends. If you write Toner 2 like Toner and 2 did in '95. You will take constant coefficients. And if you take mu in particular here, not depending on local density field, then you miss completely the coexistence phase. So if you derive a hydrodynamic theory for these systems, and we know that coexistence phase, the linear instability, which is actually in the next slide. Let me proceed. So we need this, for example. It's another reason why it's good to have a way of deriving the hydro equations, because if you do this well, you will catch this. If you don't do this well, then you don't catch this, and then you're miss. And then you have, there are less terms, but still many coefficients to play with, somewhat arbitrarily.
But what happens to the noise?
To the noise? I got rid of the noise. All this procedure, even though I got a noise term from the Dean approach, I neglected this. So I'm just in so-called mean field or deterministic limits only. Some works we have on stochastic hydrodynamic theories, but very few, in fact, I must say. And again, but this is
the Boltzmann equation is a deterministic equation. You are getting a partial Boltzmann equation.
Yeah, the Boltzmann equation. You could do the Dean approach in some sort of Boltzmann-like setting. In fact, we did that, and at the end of a day, you get the same deterministic part as the one I've showed you.
You get the noise.
Plus some noise terms.
Yeah.
Okay.
But
so
that's different from the Boltzmann equation. I mean, this is something you have got in 2 dimensions.
Well, the way we go from these Longrange equations using the Dean approach to the Shmolikovsky equation and obtain stochastic we get a noise term. We can do the same thing in some sort of Boltzmann setting. So I don't want to dwell on this now, but because my talk is anyway neglecting the noise terms, even though they could have been derived for this part, for the kinetic and hydro part. I'm setting myself in the mean field limit. And of course, real work should be done on fluctuating hydrodynamic theories, which of course is very hard analytically and numerically. So we have some bits of information on this, but right now I'm only speaking about deterministic mean field versions of these theories, which are basically kinetic equation Boltzmann type or these PDEs here. So we answer your question, Abhishek, in the last part. So this is the same equations. You see that when mu is positive, you indeed have an ordered solution. This homogeneous ordered solution, which is trivial, you know, E squared, W squared here equals mu over Xi. Good news is that Xi has the right sign from the way we derive it, and mu depends on rho in more or less complicated manners depending on the way you do it. Now you can study the linear stability of this ordered solution. So this is happening in the density noise phase diagram. This is happening between the gray and the purple region here. This is the limit of stability of a gas when you have the homogeneous ordered solution appearing via simple pitchfork bifurcation, if you want, if you stay within homogeneous perturbations. Okay. Now, what is very generic is if your mu depends on rho in a deterministic setting, then this linear solution, this homogeneous ordered solution, is linearly unstable. So you go from the gas, your order is appearing on set of orientational order at the linear level, but that emerging homogeneous solution is itself linearly unstable, and eventually at the nonlinear level leads to these bands. Now, if this is the case for the Boltzmann-derived Tono2 equation, so with the Boltzmann coefficients, the coefficients coming from the Boltzmann approach. It's so nice. There's a region of instability, which is this colored thing here. And then there's actually only a very small region of stability of the homogeneous solution, because there's another spurious instability that we have here that happens with the Boltzmann coefficient. If I introduce a little bit of positional diffusion in the problem, which I have good reasons to do, this region shrinks but does not quite disappear, but still I have, you know, a fairly large region of stable ordered homogeneous solution at the mean field level here. If I consider the Smolnikovsky-derived or Dean-derived values of coefficients, I have nothing like this. The solution is, the homogeneous ordered solution is linearly unstable everywhere. And I don't, whatever I do, even with diffusion, I do not have a region of stability. So this is rather ill-behaved. The equations are formally the same, but the values of coefficients you get are leading you into some totally unphysical region, so to speak. Now that's the linear level. At the nonlinear level, of course, I have no time to derive this, but this is things I've said already. So you have, for the Boltzmann case only, because in the Smolnikovsky case, I have nothing like this. For Boltzmann case only, I have in dashed lines now the linear stability limits that I've just shown you. So in between the two, I only have inhomogeneous solutions, so some sort of, you know, band solutions or band trains, etc., etc. But these things exist and are stable beyond these linear stability boundaries, beyond the spinodal lines up to what we would call binodal lines using phase separation language, so that the true phase separations, phase transitions that you see in fluctuating systems are actually closer to this. The real transitions are here. So the linear stability of homogeneous solutions does not give you the right answer. You know, what you have to study is a much more complicated problem of stability, coexistence, to noise of inhomogeneous solutions which coexist. So it's complicated, and we don't know how to do this exactly, of course. Finally, I would like to show you the behavior of the kinetic equation. So you can, these hierarchies that I've shown you, you can simulate this numerically. with fairly large, comfortable accuracy. You typically truncate with 20 to 40 modes. It's easy. So now you simulate 20 coupled PDEs. Okay. And if you do Boltzmann and Smolikovsky simulations, for Boltzmann, you find the right kind of phase diagram. You need to put a little bit of diffusion to recover very clearly the right, qualitatively right shape of a phase diagram. So there's a new branch here of solutions at zero diffusion, which I don't want to talk about now because I have no time. This is for the linear stability of the homogeneous solution of the kinetic equation. For the Smolikovsky equation, so forgetting about the noise term again, the homogeneous solution happens here. There's only one parameter of the density. The onset is here. And from onset until whatever you want to do, the homogeneous ordered solution in the kinetic Smolikovsky equation is also linearly unstable, even if I add diffusion. So definitely the Smolikovsky equation is ill-behaved, I would say, and this is confirmed at the nonlinear level because we can do simulations now of a full hierarchy, not just linear stability of this solution. And in the Boltzmann case, in the Smolikovsky case, we cannot get anything. It always blows up, even for what I would call here ridiculously high resolution. So there's something structurally wrong in the Smolikovsky equation. Whereas Boltzmann equation, with a little bit of care, you can do simulations of and you find very sharp bands. This is an example here with 2 bands and some idea of how the fields F1, F2, F3, F4, F5, etc. Are ordered in space, are organized in space in a typical profile. The band profile is here in black, very sharp. This is a different type of solution of the Boltzmann equation. And this is to show that the dynamic global sort of view as these things as periodic solutions of some underlying simple dynamical system is still true. You see the bands and you see also the heteroclinic orbit and all the same structure that I very briefly described to you holds at the Boltzmann level. So the Boltzmann equation is relatively well behaved, has no spurious instability that I mentioned above, and contains all kinds of solutions that we see physically, at least at the mean field level here again. Okay. So I'm already at the conclusions. I'm sorry to have sped up so much, but otherwise it would be a mess. So there's a list of conclusions. So I hope I've convinced you that even the simplest of some of the simplest of the simple DADAM additive matter setting, these models can show all kinds of interesting, unexpected phenomena. There are many, many papers at the hydrodynamic level, but most of the time, almost no exact results. And even when it's not exact, very works connecting in some sort of systematic manner to the microscopic level, which is a problem in my view, at least. Now I've shown you that if you want to connect microscopic level to hydrodynamic level, you can do this via kinetic equations and some Ginzburg-Landau scaling approach. And this has been studied in some detail by us at deterministic level again. A general message is that the Smolikovsky Fokker-Planck type of approach seems to yield ill-behaved or maybe even ill-posed equations at the kinetic level and so on. So Boltzmann typically gives better results, but of course all this at best is in qualitative agreement with the macroscopic starting point. So there's room for exact or quantitative work being done, even on simplified models such as lattice gases. There's very little being done, and it should be done actually. It could be done by some of the people in this audience, I'm sure. Okay, that's where we are right now. Sorry. Thank you, if you're still there.
Thanks a lot, Hugo, for this really illuminating, beautiful talk. So any questions? Yeah, you can raise your hands or just unmute yourself and go.
Go ahead. No, go ahead. Somebody else raised their a hand. Let them talk.
Yeah, Julian.
Yes. Okay. Can you hear me?
Yeah. Sure.
So thank you very much for this talk. I'm really puzzled by the bad results about the Smolichowski equations.
Yes.
Actually, one thing is that I would expect that this kind of local mean field approach would become exact in some mathematically well-defined limit. And maybe you are far from this limit, but can you explain more about this strange behavior?
Not much more. My way of answering that question so far has been, if I'm serious, I think about the Vicshag model or models, microscopic models like this in 2D. Typically you're going to have, let's say, 6 neighbors. You're really interacting with. So 6, maybe closer to 1 than infinity, and so that's kind of a joke. But yeah. You do, the bad thing you do, which is factorizing the 2-body or many-body probability, it's very bad anyway, because once you are aligned, you have some interaction, you align, and you're not going to decorrelate from this event any soon. And which, in a Boltzmann setting, it's very clear that molecular chaos is bad, and actually that should not apply. Nevertheless, we proceed because we hope the Ginzburg-Landau approach will yield a qualitatively correct, well-behaved set of PDEs, and it does. Now, from a Smolichowski viewpoint, you also have to factorize the many-body probability thing, and so you do this by some power of a one-body function. That's equally bad, I would say. Now, why one is still qualitatively okay and the other is not, I don't have a good physical explanation for this. Mathematically speaking, I'm sure some people would know. I mean, looking at the Boltzmann, at the structure of a hierarchy, for example, and the way we know things, we know how it is, the ordered solution exists, but it is linearly unstable in the Smolichowski equation. And we haven't looked at this in much detail, but in principle, we know which sort of mode and how this happens, etc., at the linear instability of the ordered solution. Nevertheless, we did simulations because it could have been, unstable everywhere linearly and still producing reasonable solutions at the nonlinear level of solutions of simulations of Smolichowski, but it doesn't. So we believe there's some structural problem. I'm not a mathematician enough to know this, and physically, I would say initial bet would have been for me that, okay, they should give more or less equally okay, qualitatively reasonable results, but it doesn't. And we have other cases like that also in other systems, as soon over classes, over models where you have propagative modes, basically propagative solutions, or a V grad V kind of term come in, they suffer from this. The purely diffusive cases like the active pneumatics, then, if I'm not mistaken, both Boltzmann and Smolichowski give reasonable results. If I'm wrong, Benoit, you just say something, but I think it's true. So for the propagative cases, we do have this evidence that Smolichowski-Fokker-Planck misbehaves. Sorry, not to be able to give you a more precise answer.
Thank you very much. It was quite detailed. Thank you again.
Shriyam, you had a question?
Yeah, actually, I had sort of 2 or 3 comments. One is that the fact that the density dependence of the linear term in the Ginzburg-Landau emerged only after someone did a microscopic theory, you will admit is an accident of history. A coarse-grained theory would have said generically that term is present, and in principle, therefore, it is a sort of historical accident.
Yeah. No, as soon as you say it is a compressible fluid, you
right.
have for this.
Right.
You have to have a linear term, though. You have a linear term, but you can expand, It's almost
Sure.
always there. You would need a very, very, very special symmetry. So something I did not say, but I can say now, that you probably already know, is that if you were to derive a theory that has no rho dependence, like Monsieur Degon is doing, for example, using so-called more exact methods, it's bad, but it's not so bad, because now if you put back noise, one way or another, whatever you do, if you put back noise, you see that fluctuations generated by the noise will dress
right.
linear term so that it recovers a linear variation, or at least a linear variation with the density. So at fluctuating level, this is one result we have. Even though you may have started from the wrong mean field equation, you will recover addressed rho-dependent linear term in your V equation.
Right.
And then you're okay. So that's a recent PRL, by David Martin and many other French people. But so that's not too bad. But we only know this since recently for sure, in fact. And we all suspected this. But,
right. So a second small comment, which is that it's true that you can get many of the qualitative features right by looking at the deterministic hydrodynamic equations that emerge from your Boltzmann treatment. But in principle, especially in the ordered phase, in the presence of noise, the predictions of fluctuating hydrodynamics are different as regards, as you pointed out, the peak widths and so forth. So in some sense, there's something qualitatively wrong with doing the noiseless theory for the broken symmetry phase.
Yeah. I didn't say it, and maybe it was written somewhere. I think I wrote it somewhere. The simulations of the Boltzmann equations, so deterministic with many fields, or not so many, in fact, they also show coexistence of many different band solutions, including the macrophase separated heteroclinic orbit thing. So you don't, this degeneracy, which is at the deterministic level, is not lifted by considering infinitely many. I mean, we don't do this numerically, but as many as you wish fields, what we see at the Boltzmann level, even though we are not able to do a proper simulation with infinitely many fields, of course, we can do this by this hierarchy, or direct simulations that Frey and company have done. Also, they all lead to show that you have the same problem of non-selection that you have at simple hydrodynamic level.
Nice.
So still, adding noise. So the Boltzmann equation contains more solutions and is better behaved than the derived hydro equations at deterministic level, but still missing something that you recover immediately if you put a bit of noise in the hydro level. So that should make people like you and others think. That's one key problem we have for sure. Yeah.
Right. Thanks.
Okay, so I think Shankar has a question.
Yeah, just one question. This, in case of normal fluids, there is this ENSCOG model, like you put structure of the fluid, and then you get more results or improved results. Now, in this sort of model, can you try to look at if there is a structural part to the dynamics?
Yeah. If the works Thomas Ihle, IHLE, has been struggling early on with an Chapman ENSCOG approach to a Vicsec model, where, as you may know, you can treat many body collisions. So the interaction with an arbitrary number of neighbors can be taken care of. So that's much more complicated. At some point, you still have to do molecular chaos hypothesis, unless, he also did something where he kept the two-body function, so even more complicated. But okay, the two-body function, you still have to factorize it because you have a three-body or four-body, whatever terms coming in, and so when you do this, you do a very strong approximation and which is only valid in some non-physical limits of super large nominal speed of particles, for example. And something that Euler is not doing and should be doing is, so when in his first papers with Enskog, he arrived at a hydro equation, so again, mean field, deterministic field thing, with many, many terms, some of them at order 5 or 7 in our counting. And that thing is ill-behaved. If you try to simulate this, it blows up. So without the control of the Ginzburg lambda control on what minimal term you should keep, this is not working. But if you take the Euler thing, apply Ginzburg lambda scaling like we did, of course you get again the same Toner 2 equation with different expressions for the coefficients that you have. And for that thing, we didn't do the analysis, that we didn't do simulations of the equations using, say, the Euler and Skog kind of parameters, but could be done. I'm not sure whether it's better behaved than the Boltzmann or the Shmolikovsky. It should be similar to Boltzmann, I think, but we haven't done this.
Thanks.
Okay, so and then maybe last question. You're muted. Oh, no.
Sorry. So this is going back to the patterns at the beginning of your talk.
Yeah.
So are these simulations in the presence of noise, or in the is it just a deterministic equation?
The simulation at the beginning are just Vicsec model.
Okay, so they're actually just Vicsec model.
Probably the exotic configurations I've shown are mostly angular noise Vicsec, discrete time. We have checked that. We have checked that at least some of these also exist with continuous time, and we haven't even checked that it's also the same with so-called vectorial noise. But I'm pretty sure it's very robust. It, at some point I was worried it might be an effect of discrete time, but it's not. So they do exist, and we do see them in some hydro simulations with more terms, or some very coarse truncation of Boltzmann. We can see them. So
what I was wondering is, when you said different patterns coexist at the same time, is it simply that it hasn't yet had the time to settle down into one particular pattern, or?
Well, to me it looks like, at deterministic level, from these more complicated theories than just Toner 2, these are just coexisting solutions of the PDEs with different basins of attractions, etc. Now, in the fluctuating world, it looks like it's the same, but of course there are fluctuations, and numerically, they coexist. And you run these things for 10 to the 6, 10 to the 7, 10 to the 8 time steps, and it's still there. And then you stop because, come on, we have better things to do in life. You do 1,000 by 1,000 and 2,000 by 2,000 and 20,000 by 20,000, and it's still there. Okay, then you stop. But then maybe in 20 years, I come back and say, now I can do 1 million by 1 million. See, But so the thing is that the numerical game, it seems to be endless, and at the theoretical fluctuating level, for these inhomogeneous things, we really do not have much, okay.
Yeah, thanks.
That's my best answer. Sorry.
Okay, so I think we need to stop now. So thanks again, Hugo, for this really beautiful talk. And we'll meet again in 6 minutes.